Continuar falando sobre esse assunto de superfícies mínimas, superfícies de curvatura média constante, em variedade de dimensão 3. Mais ou menos esse é o assunto. E o assunto está motivado, por exemplo, pelo esse problema. Eu falei um pouco sobre isso na última palestra, ok? So, quando você tem uma variedade de dimensão 3 e um domínio liso, compacta na variedade riemanniana, então você tem domínio chamado uma isoperimetric domain, um domínio isoperimétrico, se okay, that's fine too. It's easier. Well, okay, maybe we should, okay, so I can do whatever you want to do. I'll speak English slowly. Okay, that's fine. So I'm looking at isoperimetric domains. So those are smooth, compact domains in the manifold we're looking at, which have, for their volume, they have least area on their boundary. Okay, and we talked about, at least mentioned this last time, and I'm going to talk a little bit more about it. Okay, so I decided to come back and say a few more things. One of the interesting properties, or one of the interesting class of manifolds that one looks at in the subject are homogeneous three manifolds. So homogeneous means that the group of isometries of the three manifold act transitively. So the metric looks a little ball around a point. And you take 2 points, the local geometry is the same around any 2 points. Okay, so when you're simply connected, and we can get simply connected by going to the universal cover. So if you have a locally homogeneous manifold that's complete, and when you lift to the universal cover, then you get a simply connected, complete, homogeneous three-manifold. Okay, being homogeneous always is going to give you complete, right? So if you are one of these manifolds, then we'll probably go through and check this and show you why this is true later. But for the moment, we'll just assume it's true. Either you're a round sphere, which is certainly homogeneous, cross product R, so the Riemannian product, like a cylinder. So you take the two-sphere in R3, cross it with R in R4, you have the cylinder in R4. So that's certainly homogeneous. Or you are what's called a metric Lie group. So that means a Lie group with a left invariant metric. So you pick a metric at a point, and you left translate that metric by left translation in the group. Okay, and this is a result I was talking about last time. I added something small here, but one of the conjectures that motivates a lot of what I work on is this particular conjecture. It says if you're a homogeneous three-manifold and you're diffeomorphic to R3, so immediately comes to mind what are the different topologies for these homogeneous three-manifolds. Certainly you have spheres cross R, but if you're a Lie group, you're R3, or topologically, you're the three-sphere. So there's one Lie group that's simply connected and compact, which is which is SU2. Lots of different ways to look at it. The three-sphere, we can think of as SU2 with a left invariant metric. Okay, or we're in R3. So this is covering essentially more than half. There are lots of different Lie group structures in R3, so turns out you have lots of homogeneous metrics. Okay, partly because of that. Okay, so isoperimetric domains in X are balls. That's a basic question. We really would like to know that. More generally, we'd like to know that if you have a closed H surface embedded in such a space, topologically R3, homogeneous metric, it must be a sphere. And that would be nice. That would then show that the isoperimetric regions are balls. And the other one is that if you're in this Lie group, R3 with this left invariant metric, then the isoperimetric domains are unique up to left translation. So there's only one way to solve this problem. So if we're in standard R3, we know this, round spheres. If we were in hyperbolic 3 space, we know this. Again, round spheres, or rather geodesic spheres. Take a point, look at all the points of fixed distance from that point. You have lots of symmetry, like hyperbolic space. It's forced to be a round sphere. Okay, so I'm going to elaborate a little bit more on these things. And I thought it best maybe I would introduce these invariants, because we're going to be talking about them later on. And my talk is still an introductory sort of level talk. I'm going to talk about some proofs today, but I'm still just trying to introduce some of the concepts and examples. So there are two very important numbers associated to non-compact 3 manifolds. So one of the numbers is this number h of y. Okay, it's a pretty weird number. It's defined to be, you look at closed immersed surfaces in the 3 manifold. Each such closed surface has its mean curvature function. So think if you want oriented surface, and if you don't care about being oriented, we're thinking the absolute value anyway. So we're taking the absolute value of the mean curvature function. It's non-negative, so it has a maximum value, okay? And now I take the minimum, the infimum, over all of these numbers. And that's called the critical mean curvature, okay? Now, if we're looking at, anyway, so of course it's very simple. These numbers are very simple if you had constant mean curvature. So somehow this number is very closely related to constant mean curvature surfaces, but it's not clear from the definition exactly how. It's pretty vague. Okay, so, but it's called the critical mean curvature. It's a fundamental number associated to all the spaces. So if you're looking at constant mean curvature surfaces of constant mean curvature 1 in hyperbolic space, this is a magic number. These surfaces are just satisfy all kinds of very interesting properties that other constant mean curvature surfaces don't. So this is a special number when you're looking at constant mean curvature surfaces. Special in lots of ways. We're going to see at least some ways today. There's another very important invariant, which we were just talking about, this sort of ratio of area of a boundary of a smooth domain divided by the volume. So if you have an isoperimetric domain, then for a fixed volume, this is the smallest number for that volume. So if you can solve the isoperimetric problem, then for each volume you have a number, which is the area of its boundary divided by the volume of the domain. When the volume is very small, isoperimetric domains are almost little balls, almost little round balls. Okay, by rescaling argument, you can see this, and then that number is very big. So when you're very small volumes, we aren't getting that number. And what happens for some manifolds, you never actually achieve this number. Okay, so if we're thinking more in the case of non-compact manifolds Y. Okay? So you might get close to the number, but you only get close to it as the volume goes to infinity. Okay, so if you're in of course it could be 0, right? You can also make it be 0. If you were compact, you could certainly make this number be 0. So anyway, if Y is simply connected homogeneous 3 manifold, then you have this nice equality between these two numbers. So again, what is it, for example, the Cheeger constant of hyperbolic 3 space? You might want to think about what Lie group is hyperbolic 3 space. And once you know the Lie group, it's pretty easy, at least in the case of it's a semi-direct product, it's pretty easy to understand this formula, how you get this formula. So hyperbolic space, or more generally, if you take a non-unimodular, simply connected Lie group, like hyperbolic space, then it's relatively easy to read off from the group structure what the Cheeger constant is. Group structure together with the metric at the divinity and the tangent space at the divinity. So you can, so for hyperbolic space, the number is, the Cheeger constant's 2, right? And the critical mean curvature is 1. Okay, so it's pretty easy to calculate in most cases. There's only one place that's really hard to calculate that. I mean, hard to prove the theorem. But anyway, there's some interesting aspects that come up in the proof of the theorem. So one of the things that you see, so when you do the proof, it's very interesting to look at what are called H of Y foliations. So somehow in the proof, one shows that a Y that's simply connected and homogeneous, and say R3, then you have these foliations of it by surfaces of critical mean curvature. Okay, so let's again look at what is the Cheeger constant of R3? Pretty easy to see. Isoperimetric domains are balls. The area of a ball is like, is it 4/3? Anyway, it's some number. Is it pi r squared? What is it? Basically, it's r squared. And the volume is like r cubed. So what happens when the volume gets large, this ratio, this isoperimetric ratio, this formula in the first sort of block there, gives you that the Cheeger constant for R3 is 0. And of course, I mean, it's not hard to see. You have round spheres. They have, for example, mean curvature going to 0, like 1 over r. So when you take the infimum of the numbers 1 over r goes to infinity, you also see that the critical mean curvature is 0. So it's easy to see this formula is true in R3. And it's also easy to see it's true in hyperbolic space. Okay. Okay, so like I said, one studies what are called these H foliations. So in R3, H of R3 is 0. So we're just looking at minimal foliations of R3, and those are planes. We have a foliation by horizontal planes. In hyperbolic space, we have, for example, here's the model for hyperbolic space. You have all the horospheres at a point. Okay, that's an example of so if you're in hyperbolic space, just the horosphere foliation, fix a point here, the horosphere foliation gives you one of these very special foliations. And basically you prove that if you're R3, you always get one of these, somehow a nice foliation of the 3 manifold, of the simply connected 3 manifold by these surfaces, and that helps you prove things about the manifold. Okay, so one of the key things you prove is that if you have a sequence, if the volumes of the isoperimetric domains go to infinity, then the mean curvatures, they actually converge to the mean curvature here, but they're always bigger than or equal to. And if you're in the interesting case, non-compact setting of R3, in fact, this is always strictly bigger. You never achieve the critical mean curvature if you were R3 topologically. S2 cross R, you do achieve it. They're minimal spheres in S2 cross R. Okay, so that's one of the very useful things that come out of the proof. Another interesting thing, which I find extremely useful, and probably useful for trying to prove that last conjecture, this is very useful, is that if you, too many parentheses, if you look at what's called the radius of one of these isoperimetric domains. So what's the radius of a manifold with boundary? That's also going to be important for us various times during the course. What is the radius of a smooth compact manifold with boundary? It's the maximum, so the radius is the maximum distance to the boundary of the domain. If you have a compact manifold with Riemannian manifold boundary, you can just look at the maximum distance to the boundary. And this corresponds to, if you were in the plane, right, that's the radius of a disk. It's a distance from the center of the disk to the boundary of the disk. So it does correspond to some familiar notion of radius. So each of these domains has a radius. Then this is very, very important. It says that these domains, these isoperimetric domains, when their volume goes to infinity, somehow they have a big Riemannian balls in them. They're points which are somehow inside. It doesn't get close to itself somehow over and over again. It has some kind of nice general behavior. And that's very, very crucial for proving this kind of estimate here. So I don't think we'll go through this proof, but we might go through parts of the proof because parts of it are very elementary and interesting. There's something called the isoperimetric profile in a manifold, and we might study that at least a little bit in this course. I'm not sure what we'll do, but we might study some basic properties. Okay, so here's our conjecture that we had a minute ago. But I want to add one more interesting property. So this is something, again, we really would like to know holds. And when you're topologically R3, you're homogeneous, we would like to find something like what we have in hyperbolic space. So here's hyperbolic space. If you pick a base point, P, sort of a center for the space, you can look at round spheres. So you could foliate the complement of hyperbolic space away from a point by geodesic spheres of that radius, of varying radius going to infinity. Okay? You can do the same thing in R3. I should have started in R3. You have the origin. You just look at round spheres, and at the origin, you get this nice foliation. Well, it turns out when you get such a foliation by spheres in the homogeneous manifold, it's not hard to prove that the spheres are locally stable. So if the mean curvature is going up like I have it, kind of, or going down, it's not too difficult to prove that the spheres are what are called weakly stable. So remember, to be constant mean curvature means you're a critical point to area with respect to volume preserving deformations. If you want to make that a local minimum with respect to volume preserving deformations, we call it weakly stable. At least to second order. We can't see to second order, we can't decrease the area with respect to volume preserving deformation. So it turns out when you have such a foliation, I don't remember exactly the proof, but I remember proving it, then you're always going to be weakly stable. So again, that supports the idea that perhaps these are solutions to isoperimetric problems. If you can find such a foliation, then maybe they're all solutions to the isoperimetric problem. And the balls that they bound are the domains. And you've got a very nice picture of the space. Okay, so this is a really basic question. And one thing we checked was if you have dimension greater than 3 for the isometry group, like hyperbolic space, for example, then you can prove this result, that you have this nice foliation of the manifold. So if you're in, for example, nil with the nilpotent group with its usual metric, it has this interesting foliation by constant mean curvature spheres. So it's not like obvious. Even if you know their surfaces of revolution, it's still not like obvious. But anyway, yeah, but you do have such foliations. Okay, all right. Right, okay, so that's, I guess, the thing. Okay, so suppose you have, so now I'm going to look at the case. Suppose we are topologically R3, and I look, and we have a base point, okay? And we have a one-parameter family of these spheres, okay? Which go from the critical mean curvature, they don't ever achieve it, But when the volume's really big, we have something like, imagine, like a big, small mean curvature, and we go out to infinity, that means they're shrinking down. Right, and I want to look at a surface. So if we have such a foliation, I claim it helps you understand all properly embedded surfaces whose absolute mean curvature function is less than or equal to this special number. So we're looking at, this is the mean curvature function of the surface. I'm assuming it's properly embedded. Oh boy, I messed up here. Okay, I messed up because I should have moved the PDF file to the other thing. Anyway, okay, so we have this inequality on its mean curvature function. Then each component of the complement, there are two complements of the surface in the space, then each of those components are one-handle bodies. I talked about this in the case of R3 before. So R3, the critical mean curvature is 0. So there's no leeway here. We have to be talking about minimal surfaces, because if the mean curvature function is less than or equal to 0 in absolute value, it is exactly 0. So we're looking at minimal surfaces. And then we went through a proof, sort of a Morse theory argument, that showed that each of the complements are made by starting with a ball and attaching a proper family of open one-handles. And that's how we build the manifold. In particular, we have we have a free fundamental group for each complement. In the case, okay, that Morse theory argument actually gives you more information. For example, there are two spheres, there are planes properly embedded in R3 that are not standardly embedded. They're weird. They're just weird planes. They do something weird at infinity. Standardly embedded means after a diffeomorphism of the space, it would be the standard plane. So they're somehow weird as they go to infinity, and still they're proper. So weird things can happen, but with this Morse theory argument, in fact, we can control what happens on an end, which is an annular end. So if you have one end on the surface, finite genus, that means after some compact ball, what I see is like an annulus somehow. After some point, I just see an annulus. And we can understand how to push and pull that annulus to see that it's standardly embedded. It's not knotted at infinity. And then this one-handle body decomposition shows that, in fact, there's only one way to put the surface in this topological R3, and that's the standard way. So what's the standard way is you just take a plane, and in the standard way, you attach a finite number of handles. Or if you like to do it this way, you think of taking almost like a cylinder and just adding, and then from this point on, it just goes vertically up. So this is what I mean by standardly embedded. After diffeomorphism of the space, it's only one picture topologically. So that's interesting. So once you have this foliation of spheres, you start getting lots of insight into fairly flexible surfaces. This surface in general, like in hyperbolic space, doesn't need to have constant mean curvature less than or equal to 1. It just needs to have absolute mean curvature function less than or equal to 1 to apply the theorem. So when h, the Cheeger constant, or the critical mean curvature of the space is positive, we have very flexible theorems. We don't have to say constant mean curvature to get interesting properties of surfaces. So that's something to keep in mind, okay? So it's useful, it'd be nice to prove our conjecture that you have this foliation of the punctured space by spheres. Okay. Okay, so I guess, oh yes, this is another theorem I thought I maybe just mention here rather than later. Okay, so we have this result of what are the two spheres of constant mean curvature in S2 cross R, and it turns out they're all embedded, and but they don't converge real nicely to the minimal two-sphere. So the minimal two sphere are the level sets of the different spheres at different heights, and somehow the constant mean curvature spheres kind of cover it in not such a nice way. But anyway, for each mean curvature, there's a unique minimal sphere, constant mean curvature sphere. Okay, for each non-negative number. And they're all surfaces of revolution. So we'd like to know what happens in the other cases. In the three-sphere case, in other words, topologically you're the three-sphere with a homogeneous metric, then something nice happens. But we're first going to look at what happens in R3. So R3 is where we have lots of interesting geometries, lots of these homogeneous metrics. So in that case, it turns out this special number, which is the critical mean curvature, from that number all the way up to plus infinity, those are the possible mean curvatures for constant mean curvature spheres. There's one of them for each value, and they vary in an analytic way. Okay, and we'll maybe come down to the very end. I probably should have done this first. Every H-sphere in such a space has what we call a center of symmetry. This is also true in S2 cross R. If it's not minimal. Anyway, so we have a center of symmetry, and what that means is there's a point in the space, if it's R3, it's uniquely determined, and all the symmetries of that point, ambient symmetries, are actually symmetries of the sphere. So that's called a center of symmetry of the sphere. This is also related to the fact that the spheres bound balls, right? They're Alexander embedded, and somehow this is kind of like the center of mass for the ball that they bound. Okay, all right. Okay, so for R3, we have this nice parameterization of all the constant mean curvature spheres. S3, we have a unique sphere for each value of the mean curvature. And here it's actually interesting to think of the mean curvature going from minus infinity to plus infinity, like on the two-sphere. You do this with geodesics. You have little circles converging down to the south pole, but think of them as all being oriented. You get to the great circle here, which is minimal, right, geodesic, and now so I guess we go plus infinity up to, well, it depends on how you orient everything, but up to minus infinity. So it's sort of more natural in the three-sphere to look at examples where the mean curvature changes sign. So there's actually a one-parameter family that just continues here. It's an analytic family that somehow just continues. And in fact, you can prove the minimal sphere in this picture is always embedded. So general constant mean curvature spheres in the three-sphere with a homogeneous metric are not embedded. But the minimum one is. So in this family, and therefore all the ones close to it of constant mean curvature also are embedded. All right, so anyway. Okay. Also, this kind of result just doesn't work well at all for like constant mean curvature tori. So you might think, well, the Lawson conjecture was solved, which means if you take the round three-sphere and you're looking for an embedded minimal torus in it, use the word embedded, then there's only one. That was the Lawson conjecture, which was solved by Brindle. But you can ask a similar kind of question for like minimal tori in other metrics. And if I remember correctly, the three-sphere is special. All the other homogeneous metrics on the three-sphere, if I remember, have at least 7 minimal tori in them. Right, embedded minimal tori. I don't remember exactly, but there are a bunch of them in general. Or maybe you have to assume 4-dimensional symmetry group, but I don't remember exactly. But anyway, when you go to tori, things are just not very good. Okay, so in the three-sphere, since we have this nice family, it's not hard to see that you have a bound on the areas of all constant mean curvature spheres. Okay, they're all Alexander embedded. And that's because, let's maybe go through and check why they are all Alexander embedded. So if you have this analytic family, This is an important proof technique, so I'll just go over it. So initially, you are embedded. They're little round balls. When the mean curvature is very big, I understand the geometry of these little spheres that are bound little round balls. And they kind of go converging down to a point. And during the deformation, you can look at this immersion of the ball into our space. So we can look at the immersions of these balls into the space by the parameter, which is the mean curvature of its boundary. Okay, so initially we have these little round balls. They vary in a nice way. Now what goes wrong? If I move the boundary a little bit, then of course, now the ball, here's the ball, maybe the ball passes through itself, right? But because you have positive mean curvature, let's stay away from 0 in this argument, then you can't somehow try to touch yourself. And these, so we're thinking H positive as a boundary of the ball. They can't somehow try to touch themselves in the inside because they're mean convex. Okay, and then you can contradict the mean curvature comparison principle, or it's like a maximum principle. So as you move surfaces with positive mean curvature to new surfaces of positive mean curvature, and they bound regions when you do initially, then these regions just continue to move and stay embedded or immersed. Okay, they can pass through themselves, but the immersion, the ball, is still there. So that's what we mean by Alexander embedded. Okay, they bound it in an immersed ball. Okay, and you can, if you assume that H is positive, then that ball is mean convex. Okay. All right, so that's one of the things we want to do. We talked a little bit about this last time. I just want to remind you of a picture. The classification of genus 0 minimal surfaces in R3, which are properly embedded. We have these examples of Riemann, which look like an infinite stack of planes joined by little tubes, and the tubes go off diagonally. So this is a surface of invariant under translation, and the translation has a skew part to it. It's not just vertical up translation, it's up and over, up and over. So there's a diagonal sort of translation for these surfaces, and that's the classification. So some of the things we're going to be looking at are going to be constant mean curvature annuli, for example, inside of certain 3 manifolds. We're going to try to understand some properties when they say a constant mean curvature. So I'll talk a little bit about that today. We had this important notion of proper last time. So proper just means in the space you see a compact part of the surface and a compact part of the space. Okay, and we also saw that properness implies completeness. It's just a stronger, possibly stronger property than completeness. And we were basically in here. So let me just review real fast. The genus of a surface is the maximum number of pairwise disjoint simple closed curves. It may be infinite. Finite topology surfaces. They are just taking a closed surface, removing a finite number of points, equivalently finitely generated fundamental group. Okay, so finite genus, finite number of ends. Planar domains means your domain that can be parameterized by the plane. And okay, all right. And we had this sort of nice. Let me just go here. We had this sort of nice result that says it's kind of like a Morse theory. Imagine like a Morse theory, Morse function on the surface. So think of this Morse function as being the distance from a particular point. Okay, so as you go over here, you somehow exhaust the manifold by balls of integer radius. And suppose that those integer values were kind of like, nice values for the function, like in terms of Morse theory. But anyway, this is supposed to mimic that. It's somehow a smooth exhaustion of the surface. And we have it defined inductively. So the first, we start out with a ball, then we go to maybe a pair of pants, or we attach a handle and nothing interesting here, or maybe we attach another pair of pants at the next stage. So we have this sort of nice picture. And that really helps us classify surfaces. So for example, suppose you have one end and infinite genus. What is the surface? Well, we just take the picture, okay? Now, notice if you have one end, each time we split, each time we add a pair of pants in this picture, that gives me a new way to travel to infinity. So we're going to be talking about ends, but in some kind of sense, you can see, as long as I don't add any pair of pants in this picture, I have one end. And if I have a pair of pants, don't have one end. So that means we're very restricted when we make this picture. So there's only one picture we can make. I'll draw it vertically up since I know how much space here. But we start out with a disk. Then we have genus 1. And then we have genus 2. Right? At every stage, you add one handle until you run out of topology. In other words, nothing changes after this stage. So if I had finite topology, I would just do this a finite number of times. And the number of these handles I attach would then be the genus. Okay? And if I have infinite genus, here it is. There's only one picture you can make, and therefore that's the surface. If I have any two surfaces with infinite genus and one end, then that's the surface. There's only one way to do it. So when you have this nice picture, you can understand immediately why there's only one example of a certain type. Okay, so now I'm going to, right. So we saw the cylinder last time. Okay, so one of the things I had wanted to do yesterday, which I did not do, was to write down some slides about what are the ends of a surface. How do you define, what is an end of an open surface? And I was hoping to do it early this morning. I got up early, but I also didn't succeed in getting to that. So I'm going to do it on the blackboard, and I will write it up and put it in the notes. Okay, I'm always going back and working on the notes a little bit more. So it will be in the notes next time. Okay, so we're looking at non-compact surfaces. And I want to try to explain what it means to be an end. What is the space of ends of an open surface? Okay, so let's just kind of think of the cylinder as a good example. Okay, but in general, we have some maybe complicated surface, like those pictures we drew before. Maybe. Just imagine doing this. So I always make things trivial, say here, but on the right-hand side, I always add a pair of pants. So these just become cylindrical ends, and always the one on the right-hand side splits, just forever and ever in that sort of picture that we had before. Okay, so we want to say, what are the ends of the surface? So the ends are different ways to travel, inequivalent ways to travel to infinity. Now, when I say travel to infinity, I mean I really want to go to infinity. So I want to travel along a proper path. So I don't want to keep returning to where I started. So I want an arc which somehow eventually leaves every compact set. So I pick a base point, and I look at proper arcs. But no, base point's not so important. Anyway, I pick a base point and look at proper arcs starting at that point that goes to infinity. So I'm looking at alpha, 0 to infinity, into the surface. And I want this to be proper. Okay? So the ends, so the definition is E is an end of the surface. It's just an equivalence class of paths. So it's an equivalence class. I'll write the equivalence relation tilde of proper arcs. So then you have to decide when are two paths equivalent. So alpha 1 is equivalent to alpha 2 if for any smooth compact subdomain, omega in the surface, then M minus the interior of omega, okay? So you remove some compact part of the surface, like this part, okay? Then omega minus that, then, okay, so then the ends of alpha 1, alpha 2, in other words, the non-compact part of alpha 1 and alpha 2, they lie in only one of these components. There are some number of components here. So since this goes to infinity, it can only be in one of those components. This can only be in one of those components. And I want these to be in the same component. So the non-compact parts of the arcs are always in the same component, no matter how big omega is. Okay, so that's what it means to be equivalent. And I did mention last time there's a natural topology on the space of ends. And there's also a natural language to talk about the ends in a more geometric way. So this is sort of a pretty abstract way to think of it. It's not the way we really think of ends. So when you look at a cylinder, what do I think? I think, well, an infinite cylinder, I have its top end. And I have somehow going up, right? Everything above here is its top end. Everything below here is the bottom end. So we really like to think of ends as being somehow represented by domains. So I want to try to clarify that. Okay, so how do we make sense of that? And that we do that with what's called end representatives. So here, think of the cylinder here. Here's my proper arc, and it somehow goes up and up and up. Doesn't, okay? So somehow I want to say that this subdomain of the cylinder, it's proper, so this omega here is contained in our surface. It's proper. It has compact boundary. Compact. Okay. And alpha intersect omega is non-compact. Non-compact. So in other words, the end of alpha is eventually in this subdomain. So this would be like the top half. Okay? And if that's true, we say that omega represents the equivalence class of alpha. Remember, we have the ends are equivalence classes, and we say that omega represents this end associated to the proper arc. Proper arcs create ends, okay? And now, so associated to every end, we can talk about certain proper subdomains as being end representatives. All right? So then what's the topology on the space of ends? So let me do this sort of, I don't know, it's kind of like an E, calligraphic E of our surface. This is the set of ends. And I wanted to find a topology. I got to tell you what's an open set of ends. What's an open set in here? So I need a basis for the topology. And what I do is I just look at any one of these a proper non-compact subdomain of M, with compact boundary, and I look at all the, it's an n representative for something, well, I look at all the curves. So I look at given one of these omegas, I can sort of look at, I don't know, I'll call it E of omega is the subset of the space of n's, all these proper equivalence classes, such that their n's, such that omega represents those n's. So these are, so you pick a domain that's proper, then you look at all of the equivalence classes, all the n's that somehow are in there. So for example, if you had this sort of picture, and it just kind of went on forever and ever. So here's my omega, okay? Then in this picture, somehow the surface looks like it only has two ends. So for this omega, this would be 2 points, okay? But I declare that set to be open. I declare that to be open. That induces a topology on here, which in fact is, makes this into a compact metric space. Okay, well, actually, it's easy to say it's a compact Hausdorff space, and then you need to do a little more work to understand that in fact E of M is homeomorphic to a closed subset of the unit interval. So with a little bit more work, you can actually prove that the space of n's of reasonable objects like manifolds are always homeomorphic to a closed subset of the unit interval. Okay, so that means we can make every possible surface. We just take a curve on we just take somehow a genus, we know genus 0 surface. That was one of the reasons genus 0 is important. Look at a genus 0 surface, make a curve on the surface, and then remove a closed subset. And it turns out there's a classification theorem for these things. Okay, so let's go a little further. We also had this slide last time we were looking at it. It's kind of one of my last slides. And I'll just let you guys look at it a little bit more. I was going to correct this. This is supposed to be the two-sphere. This is supposed to be a capital S. Okay, so let's just go to this interesting example here. So here's an example of a planar domain. You say, well, how complicated are genus 0 surfaces? They can be extremely complicated topologically. So here's an example where the closed set of n's, this compact set of n's, which I can think of as a compact subset of a unit interval embedded in the two-sphere. So I take the two-sphere, I take a curve in it, like a geodesic, and I remove, and I look at a Cantor set on that curve, okay? And I claim that that is homeomorphic to this picture. So let's just see why we have an uncountable number of n's in this picture. So here I'm just keep on, as I go to the right, I keep adding pairs of pants. Pair of pants, forever. The surface is properly embedded in R3. And it's clear, to go to infinity, I have to go from left to the right. So a proper arc has to make a decision right here. Do I go that way or do I go that way? So I can think of that as, I can go to the right, I call that a 0. If I go to the left, I think of that as a 1. So a little thought shows that, so it shows that the set of n's is nothing more than a sequence, an infinite sequence of 0s and 1s. Every infinite sequence of 0s and 1s represents an n, a way to travel to infinity. I go left, right, and keep going to I go up or down, right? Up or down and to the right, always to the right. So this surface is space of n's, all sequences of 0s and 1s. That's, if you look at base 3, and you remove all those kinds of points from the unit interval written as base 3, that's a Cantor set. Right? It's a Cantor set when you use base 3. So we can see that the space of n is embedded, at least somehow, in a natural way in the unit interval. Okay, so that's, But it's complicated. It's a very complicated surface. So one of the things we wanted to do many years ago, there were no topological obstructions to the existence of properly embedded minimal surfaces in R3 that are orientable. So many years ago, we didn't have any topological obstructions. Maybe a properly embedded minimal surface could have this topology. Who knows, why not? I can properly embed it in space. Can I do it in a minimal way? And there's a paper I did with Pascal Collan, Harold Rosenberg, Rob Kussner. We proved that a properly embedded minimal surface in R3 can only have a countable number of ends. So this surface has an uncountable number of ends. We proved a lot more, but that's one of the things. So we now have these crazy topological obstructions to certain surfaces occurring as properly embedded minimal surfaces in R3. The proper is very important. Okay? And in fact, we have many more topological obstructions now. We have interesting finite topology ones. So we'll see that as we go on. Okay, so here is the classification theorem for non-compact surfaces. Okay? And let's even restrict to the orientable case. So when I had that picture of the simple exhaustion, I could have non-orientable. I could have a Mobius strip with a disk removed. So we're just looking at that very simple, nice picture where I always have a pair of pants or I have a torus with two disks removed. That's the way I think of my surface. Okay, so we'll look at those surfaces. When can you tell if two of them are the same? And this is just the classification. If they have the same genus, that's certainly necessary. So maybe they're both infinite genus. That's good. That solves the problem. Okay. And you want a space, a homeomorphism of the space of ends. Remember, the space of ends has a topology. So you have to try to organize. To get a diffeomorphism, if you have a diffeomorphism, things are organized. Proper arcs go to proper arcs. So when a diffeomorphism between the space of ends that preserves all of the ends with infinite genus. So that's a definition I haven't made yet. So what does it mean for an end to have infinite genus? And you said, well, an end is an equivalence class of proper arcs. I don't see genus anywhere. Okay. So the genus of an end must refer to the genus of representatives. Okay? So if you can find, so you pick your alpha, your n, take your equivalence class of alpha. So take alpha. We have associated alpha all of the n's represented by that. Well, if you take a proper domain, we have the space of n's. And we call such domains representatives of alpha. So if there is a representative of genus 0, we call that an end of genus 0. If you had an end of finite genus, it just means there's a representative of finite genus. There's a proper subdomain that represents that proper arc. The proper arc lies in a proper subdomain with compact boundary and has finite genus. But if you have finite genus, then you can make a new end by removing the finite number of handles, which has genus 0. So really that means every end has either genus 0 or infinite genus. That means every proper subdomain that it represents has infinite genus. Okay? Like if it has one n of infinite genus, then of course that's going to be what happens. So you need this homeomorphism, not just to be a homeomorphism between these compact, totally disconnected subsets of the unit interval, but we need associated to each of those points in here, there's a number which is either 0 or infinity. And we need to have that homeomorphism preserve those two kinds of sets. So it sends genus 0 ends to genus 0 ends, infinite genus ends to infinite genus ends. It certainly would be the case if you had the homeomorphism between the surfaces. But it's kind of the cookbook that tells you how to go backwards. If I'm this homeomorphism here with this property, and the picture we drew before of simple ends, I can go back and recreate the surface. There's only one way to make the surface. So that's some work, right? It's not real easy. But anyway, that's what happens. That's the classification. Again, it's something which I'm guessing maybe even Harold didn't know that people just don't know this classification theorem. They know for compact surfaces, but they don't know this kind of theorem. I think very few people in the world probably, if you ask them what is the classification of surfaces, open surfaces, they probably don't know. Maybe you're talking about 30 or 40 people in the world. So this is not something that even people who work in topology know very well. But it's true. What? No, there's no reference for it. You had to, as far as I know, it's never been written down anywhere. No wonder nobody knows it. For me, yeah, you had to think about it. You had to think about, I remember doing this when maybe I was a graduate student. I was thinking about problems like this. And you have to see, how do I make, the question is, how do you get from here to the surfaces being a homeomorphism of the surfaces? That's what's hard. So it's kind of, you can have a recipe. This is like a recipe for creating a diffeomorphism of the surfaces. So you have to slide things around, move things around, and think about it for a while. And the simple exhaustion certainly helps you make a picture, but it's hard. Okay, so anyway, this is, okay, so what are some simple consequences of that? Two orientable surfaces of finite topology are diffeomorphic if and only if they have the same genus and the same number of ends. So there's at least, that's certainly easy to see, right? You draw that simple exhaustion, you have a finite number of pairs of pants. You can see you can make the pair of pants happen first, or you can do all the genus first, and then you can add the pairs of pants. You can look at those simple diagrams, and if everything's sort of finite number of genus, finite number of ends, you could certainly slide things up and down and add all the handles first, and then pairs of pants. And it's easy to see that that's what you make. Okay. Right. So right. Okay. So all right. And again, finite genus are two surfaces, non-compact surfaces of finite genus are homeomorphic if and only if the space of ends are homeomorphic. Again, in that picture of a simple decomposition, you can add all the handles at the beginning. Then it's just the question of planar domains. And in planar domains, you're supposed to already understand how to do that, right? You have these just pairs of pants appearing in that simple picture. All right. So here's an example of the plane, and I guess I'm patching handles at integer values. So what is that surface? So that surface certainly has infinite genus. And the question is, I claim it has one end. How many people understand, what's a simple way to see that a manifold has one end? What happens when you have one end? It means when you remove compact sets from it, infinity is always connected. So you remove a compact set, I get a finite number of pieces. Because each, from the boundary curves, I have a finite number of boundary curves, and I create a finite number of pieces. When it has one end, there's always one non-compact piece. All the other pieces are compact. So I can't disconnect infinity from so in other words, if you take a big compact set and remove it from the surface, or rather think of it like this, take 2 points that are very, very far away. I can't disconnect them by a compact set that's near the origin. So think of here, any 2 points that are really, really far away can always be joined by a path. Right? The path doesn't have to come down and into this compact set. I can't disconnect infinity by removing a compact set. There's only one part, somehow, infinity to the surface. Harold? Oh, I thought you said something. Okay. All right. So this example, it's easy to see. I can find an exhaustion with simple closed curves, right? I could just take, I don't need to add any pairs of pants. I can just, so that picture is that picture I drew before, which was, if I redo it in the simple picture, this is what the surface is, right? So I have disk, bigger disk. Sort of intersect this with balls. Ball of sort of integer radiuses, or integer and a half radii, based over here. That precisely is one of these simple decompositions. Okay, and so you have one end and infinite genus. And here's an example. And it turns out something really fascinating happens. Okay, so it turns out before, just a few years ago, 20 years ago, basically we didn't know any examples of minimal surfaces. We knew like kind of like a finite number of examples, but almost all the examples, we had lots and lots of classical examples, but they all had infinite genus and one end. We had the catenoid, we had the plane, which has one end, genus 0. We had the catenoid, we had the helicoid, we had Riemann's examples, and that was it. All the other examples had infinite genus and one end. Okay? Pretty fixed. In other words, not much going on. Now we have lots of different topological types. We have lots of things. And one of the big questions in the subject is, what are the topological types for properly embedded minimal surfaces? Okay, so for example, we have this example. Another interesting thing in terms of topological uniqueness is if you take two properly embedded minimal surfaces, like this triply periodic example, and take another with infinite genus, and you take another one with infinite genus, then in fact, they are standardly embedded. So there's a homeomorphism of R3 that takes one to the other one. So for people who know classical examples, remove the catenoid, helicoid, and Riemann, take any two classical examples, they're not those, there's always a homeomorphism of R3 that takes one to the other one. It's pretty cool. There's no knotting going on. Okay. All right. So anyway, so here's our Schwartz example. Okay. Okay, so the next part of my talk sort of changes theme a little bit. I'm going to work a little bit more on Riemannian manifolds, and then we're going to come back to R3 again. So one of the crucial things to understand surface geometry is what's called the injectivity radius function. So just kind of show of hands, how many people know what the injectivity radius function is already? Okay, most people. Okay, good. So on a manifold, a Riemannian manifold, at each point you have the exponential map. So you have you're on a surface, you take a point, you have the tangent space on the surface, and for any vector in the tangent space, you have a geodesic on the surface that has that for a velocity vector. Okay? And if I travel time 1 with that for my velocity vector, I get a point on the surface. Okay? And that's called the exponential map. You're given a vector, and then I travel time 1 in that direction along its unique geodesic in that direction. That's called the exponential map. Okay. And of course, let me draw a bigger picture. Here's the tangent space at a point. Here's TP of M. And inside the tangent space, I can look at balls of radius r, or in case of surfaces, disks of radius r. And I can ask if the exponential map restricted to the disk is a diffeomorphism. And if it does, it sort of gives me nice coordinates projected from the plane onto the surface. Okay, so geodesic coordinates, normal coordinates, kind of these nice coordinates arise from this exponential map. So anyway, for each point, you can look at the biggest radius that works. You can look at the biggest radius such that that disk projects down to an embedded, projects in it as a diffeomorphism down to the surface. That's called the injectivity radius at the point. And as you move around, okay, you can take the soup of those. You can do this for each point, and you can, okay, and you can do the soup over all points. Okay, that will give you what's called the injectivity radius. So the injectivity radius function is the soup of when you're a diffeomorphism, when you have these nice coordinates. What? And, right. Oh, right, that's the soup of those numbers, and the injectivity radius of the manifold is the infimum of all those positive numbers. So at each point, you get a positive number. If you have boundary, of course, then this number is going to be 0. If you have boundary on the surface, then it's going to be 0. So that's something also to keep in mind. So anyway, that's called the injectivity radius. And it's related somehow to the geometry of the surface. So, right. So let's try to do this. This is going to be important for understanding certain things about minimal and custom curvature surfaces. So why is this result true? I put it as a remark, but let's just try to see why it's true. Okay, so we have a complete Riemannian surface of non-positive curvature. So one of the things one studies when one studies surface geometry, one looks at geodesics, one looks at Jacobi fields. For geodesics, one studies this exponential map. Now, there are two ways to fail being a diffeomorphism. One is the Jacobian of the differential is 0. Another way to fail is it's not injective. Right? There's two ways. So it turns out when you're non-positive curvature, the exponential map, think of it as being defined on the entire tangent space, right? When complete, it's defined on the entire tangent space. The mapping is. But that's always a local diffeomorphism. Okay? So it's always an immersed disk on the surface. The image is an immersed disk. So the whole problem of finding the injectivity radius at a point, so we see these disks and they grow, whatever, and keep on going. But maybe they're trying to start bumping up into themselves. So at some point, what happens is the disk stops being embedded. But because it's an immersion, the boundary curve of the disk is an immersed curve. And this first time that you aren't immersed, then you get that immersed curve touches itself from the outside of the disk. So remember, you're kind of these geodesics coming out of here. Okay. All right. So in particular, there's a geodesic that comes in from that side, and another geodesic that comes in from the other side. And since these curves are immersed, they're tangent at that point. So what I find is a geodesic arc here. The geodesics are always perpendicular to the curve. That's Gauss's lemma. So these are always orthogonal here. So these curves match up real nicely here. So what I find is a geodesic loop. Okay, so here was the place where we originally sort of intersected, but it produces, here's our point, it produces what's called a geodesic loop. And we want to try to understand properties of geodesic loops. That's going to be what comes up next. Okay? So any questions about how you get that geodesic loop? So loop means it's a geodesic, but here there's maybe some kind of angle here. The angle is 0, that's nice, but it may not be the angle, or there's some kind of an angle between these two geodesics. right? Maybe it's 0, maybe it's not. Anyway, you can find this geodesic loop. And it has length 2r, right? Because this happens at distance r, so this is minimizing geodesic up to here. So this arc is length r, this is length r. Our problem happened here. So this geodesic loop has length 2r. Okay, so that's pretty simple, easy to understand. Okay. All right. So now we want to try to understand the relationships between the second fundamental form being bounded and somehow the geometry of the surface and the geometry of the ambient space. So if you pick a three-manifold which has somehow its bounded geometry, so think of it, you take locally it looks like R3, a ball in R3, and you perturb the metric a little bit. So on a very small scale, I've just taken a kind of standard ball in R3 and I perturb the metric somehow in a uniform way. I don't make it too bad. Don't go too far away from Euclidean. Okay, and I assume it has positive injectivity radius, so I can do this, make these little balls at every point, and everything looks sort of like Euclidean, but it's not. But it's not. So a bounded distance away from being Euclidean. And if you look at a complete surface in it with bounded second fundamental form, then it turns out it has positive injectivity radius. And that's because you have this uniform graphing lemma, which says that in local ambient coordinates, a surface with bounded second fundamental form is a graph, a sort of a natural graph over its tangent space. We can think of exponentiating the tangent space. If it's positive injectivity radius, we can think of that as being embedded and nice inside of the three-manifold. And then you have somehow a graph over that. And then the projection sort of is nice, and you can, from that projection, you can see the injectivity radius of the surface is bigger than, it kind of behaves like the injectivity radius of a plane, which is infinite. But I mean, on a small scale, it looks like a disk on a plane. Okay, so that's called the uniform graphing lemma. Okay. All right, so now I just want to do a little experiment, a little practice with these notions in the realm of the subject of the course. So this is a slide I made right before I came here, so hopefully I didn't make any mistakes. So we'll see. Okay, so we have a complete three-manifold, and I'm going to make an assumption about it. It has sectional curvature less than some negative number, like maybe it could be hyperbolic space. It could be constant negative curvature, for example. Okay? And inside this manifold, I want to look at a complete minimal immersion of a surface which is an annulus. So this is our standard way of thinking of an annulus. It's a circle crossed a half-open interval. I put infinity there because I want to think it's complete. I want to think it keeps on going forever and ever. It's the top half of a cylinder. Okay, that's all that's going on. Okay, so we have a minimal annulus in it that's complete. Okay, what can we say about such annuli? Well, the first thing is if n has positive injectivity radius, like hyperbolic free space, it's simply connected, for example, it would have that property, then the immersed annulus has positive injectivity radius function. I probably didn't write it right. The immersed minimal annulus has positive injectivity radius function away from its boundary. What I mean is at the boundary, the injectivity radius functions identically 0. But once I go say, distance 1 away from the boundary, I can say, can I have points going further away where this injectivity radius function goes to 0? Away from the boundary means some definite distance away from the boundary. So once I go a definite distance away from the boundary, where this function's not identically 0, once you go away from the boundary, you're not identically 0, I want to say it stays away from 0. So why would that be the case? So that's one property. And let's just look at the rest of them. Okay, so how do we use these geodesic loops? Well, maybe that's not the case. Maybe there are points. Let me draw the picture. So I'm drawing the abstract picture of the annulus, okay? Right. So here's the boundary of the annulus. And then somewhere I see these geodesic loops, right? So I see these short curves. Now there are two kinds, on an annulus, there are two kinds of curves. So Jordan curves, so here's our annulus. There are two kinds of curves. Either they bound a subdisk, or they generate the fundamental group, or the first homology group. Either they go around the boundary, they're parallel to the boundary, or else they bound a disk. Okay? So let's just see in general, if you have one of these loops, think of being far away from the boundary. So in this picture, I have this sort of loop that we had before. So if the injector radius went to 0, then I would have points far away from the boundary with these little geodesic loops of length 2r. Right? I would have, and they would keep on going. I mean, okay. So here's infinity. So I would find a sequence of them, right? Going to the boundary at infinity, right, of the annulus. Okay, and I have these little loops. Well, if a little loop bounded a disk, okay, well, if you are if minimal surface in a manifold of non-positive curvature always has non-positive Gaussian curvature. So it's kind of like what happens in R3. And you get a little boost if you know the ambient space has strictly negative curvature, sectional curvature, like hyperbolic space. So in fact, the Gaussian curvature at each point becomes even at least as negative as that ambient, as its tangent space, as the sectional curvature of its tangent space. Okay, so let's just see. Harold's great doing these arguments. Unfortunately, I didn't do the argument. So here's a question: can you have? So here we have k less than I guess epsilon. So we have on this disk we'd have the Gaussian curvature is less than epsilon, and now you apply the Gauss-Bonnet formula, right? So let's see. This is terrible. I should have done this before. So we have our disk here, and the integral of k dA is going to be, it's a disk, so it's 2 pi. 2 pi times the order character, which is 2 pi. And in general, it's this plus the integral of the geodesic curvature of the boundary. So over the boundary of the disk, kappa g ds. Okay. What is the total? And of course, you also have an angle here. You also have the 0th dimensional part of this formula. Well, the angle is less than pi. This is 0 on the curve, and this is negative. So if you look at all these numbers together, you can't be positive. You can't get a positive number. So you can't form disks. So if the injectory radius was going to 0, that would mean these geodesic loops have to go around the annulus. So that gives you a very different picture. So in other words, the picture kind of looks like, I'll draw it like this. I'll draw it like a little short curve that's parallel. And then later on, it's even shorter. It gets shorter and shorter. These are supposed to be these geodesic loops, okay? But just think of them as being like little geodesics. So it somehow gets pinched, and it gets pinched, and it gets pinched. Okay, so. All right. Okay, so anyway, the claim is the generator of the fundamental group of the annulus has to be homotopically trivial in N. The mersion is proper in N. The annulus has finite total curvature. And finally, the annulus has finite area. So the only way this can happen, that the injectivity radius gets small, is somehow we're getting these, things are pinching off, but somehow it combines nicely in the manifold. Okay, so this curve has to be homotopically non-trivial in the manifold, and we got this picture. So for example, suppose we knew this. Maybe I should have definitely thought about this a little bit more. I just finished typing it. Okay, so why if n has positive injectivity radius, the second statement, then the immersed annulus has positive injectivity radius function away from its boundary. Why, if the ambient space is nice, why does this picture not happen? Okay. So, right. So let me just try to do this, thinking in the case of hyperbolic free space, where we have not only negative curvature, but we have a bound on the curvature from below, just so we have a sort of a better picture. So in this case, in fact, if you had this picture, you would have a short curve, long, a piece of surface, and then think of this short curve as being far away. So this is intrinsically far away. Okay? So one way to do this problem, there are a bunch of different ways to do this. One way is to do what's called isoperimetric inequality, apply an isoperimetric inequality, and prove that the area of this surface, so in hyperbolic space, you can prove it. You can prove an isoperimetric inequality for compact minimal surfaces with two boundary curves. In fact, you can do this in any simply connected homogeneous three-manifold that's topologically R3. So if you have a surface, a minimal surface that's compact with two boundary curves, I don't know it for three, but I know it for two, then there's an isoperimetric inequality. So if the curves are short, the area can't be very big. So small area, or at least fixed area, right? Between two of these, we can make this very small area. On the other hand, an argument that uses something similar to what's called the monotonicity formula shows that the area of a minimal surface has to grow at least linearly. So if I take a geodesic a minimizing geodesic in the manifold, then there are constants that tell me that the area grows at least linearly as I travel along that geodesic. So that's why one of the reasons I am particularly interested in what are called isoperimetric inequalities. Okay, so that's sort of one way to do it. It's probably a better way to do it. Let me think of another way to do it. Right, so it has big area. Right, so you don't need, no, here it's, right. Right. So if these curves go to infinity, then I claim, and we're in a homogeneously regular manifold, so we had the positive injectivity radius, then you have this estimate that tells you that as you travel along length minimizing geodesics, a small neighborhood of that geodesic has area that grows at least linearly. So that means the area has to go to infinity. But it can't by the Gauss-Bonnet formula, because the Gaussian curvature is less than or equal to -1, right? So when you integrate the absolute Gaussian curvature on this domain, you get some finite number. You get a bounded number. It depends on the geodesic curvature of the boundary here. But the Gaussian curvature is bigger in absolute value than 1. Okay, so it says the area, therefore, it can't be any bigger than some fixed number like 2 pi. But we said the area had to grow at least linearly. To do that, we need positive injectivity radius on the ambient space. So when you can look at things extrinsically, and everything's nice extrinsically, then in fact, one has this linear area growth property. So the area is getting bigger and bigger. By Gauss-Bonnet, it can't be any bigger than some particular number because yeah. Right. What? Okay, all right. Right. I really wish I had done this before. Okay, so we have integral k over the disk plus the integral of the geodesic curvature over the boundary of the disk plus the sum of the exterior angles, which you have 1, which is less than 2 pi, I guess, right? Go from here to here. That's the exterior angle. So some number theta, and theta is less than 2 pi, right? We go there over to there, less than pi equals 2 pi. So there's the Gauss-Bonnet formula for our problem. Right, the exterior angle is always less than or equal to pi. So what were you saying, Harold? That I should. Oh, right. So if we did an annulus, right, and we're not doing this one, we're doing annulus. So annulus, order characteristic of annulus is 0. So you're right. I should have put a 0 here. Right, theta 1, theta 2, I'm sorry. So theta 1 plus theta 2, and that's less than or equal to 2 pi. Or I guess actually, well, yeah, less than or equal to 2 pi. Okay, so this is big negative. This is 0. And so we got the integral of the Gaussian curvature plus 2 pi. Okay, so anyway, the integral of the Gaussian curvature can't be any bigger than minus 2 pi. That's what the formula would say. Therefore, the area can't be any bigger than 2 pi. But if you're in the space so that it has positive injectivity radius, then we can involve the ambient geometry. We can take coordinates. And from those coordinates, we can apply the divergence theorem. And we can create area, intrinsic area. Yes? What were you, Harold? Oh, yes, Laurent.
There's something that is not clear to me. In the last one, you still assume that n has positive injectivity radius?
No, the last point, I don't assume that. So, right. And so, in fact, it must not be the case. Right. So, if this is saying the injectivity radius function is bounded away from 0 in this case. In this case, I'm assuming it's not bounded away from 0. So automatically, by the first item, n cannot have positive injectivity radius. If it did, then the annulus would have also have positive injectivity radius, at least away from its boundary. Okay, and again, this is sort of a similar kind of argument. The surface has finite area. That's, I guess, in fact, you could have an estimate. Once you get between the two annuli, you have the original finite part. You have an area beginning. But once you have this little loop here, then you bound all of this. This is always less than or equal to 2 pi. So you have an initial amount of area here. And then from here all the way to infinity, you have nothing more than 2 pi. So you have finite area. OK. All right. And also you can see that the immersion's proper. Why is the immersion proper? So let's see if people can figure out why is the immersion proper. Well, the property of having relatively big area, yes. What? B, yeah, it's a very simple question. Why do we have, what about A? Oh, okay. Okay, how do we do A? Okay, so A is a consequence of the second statement there. So if n has positive injectivity radius, then we're good. If the generator of the fundamental group of the annulus is trivial, then I can lift everything to the universal cover of the space. That has positive injectivity radius. because we have negative curvature, essentially. All right? So it has, the universal cover has, positive injectivity radius, and then I apply this. But the annulus itself will lift up to a space which has positive injectivity radius. They're trying to understand. They have a paper that's somehow related to some of these ideas.
What you mean is that the generator is not.
Oh, maybe I said the wrong thing. Like I said, I was typing this like 5 minutes before right before I came here. The generator of the fundamental group of the annulus is not homotopically trivial. I'm sorry. So like I said, I was typing this. Even after I got here, I was still typing right before my talk. So it's non-trivial. I'm sorry. That's right. Right. So anyway, it's kind of nice. You just need a minimum amount of knowledge, Gauss-Bonnet formula, some elementary estimate about if you're in a ball and you have a surface whose mean curvature is bounded by a constant. So this estimate really has nothing to do with minimal surfaces. It has to do with any surface which has a bound on the norm of its mean curvature. So if you look at a surface with mean curvature, less than or equal to 1,000 in absolute value, you can apply that the area of little disks actually is something. So that's kind of you have to use a divergence argument. It's an elementary calculation. But you really don't need minimal to get this, that the area has to grow linearly. It's really a property of doing everything in a certain coordinate system, which you have if you have positive injectivity radius. And then proper, why are you proper? So let's see. What? No. Why is the mersion proper if its injectivity radius function is 0? Why is if you go to infinity, you have these short curves, why is the annulus automatically proper? If it's not proper, that means it accumulates around a point. Not proper means there's a little ball in the space with an infinite amount of area in it, right? Or we have the surface accumulates, but now we're in a coordinate system, so each of these little pieces that come through the coordinate system have to have a big area. You have to keep area. You have to actually have an infinite amount of area and a little ball around the point where it's not proper. But we said we have finite area. We actually estimated the area as some initial finite amount and another amount which we can estimate by 2 pi. Okay, so we're automatically going to be proper. So what's nice is this is very simple, elementary, and works for immersions. We don't need to assume embedded. Okay, so. But we have small loops, right? No, not if the injectivity radius of the manifold is 0. Okay, so Harold. Only if the injectivity radius of the ambient manifold is positive. So, for example, Harold and Laurent, they like to look at minimal surfaces which are annuli inside, like these annuli, which are inside hyperbolic 3 manifolds of finite volume. Those manifolds do not have positive injectivity radius, right? So they like to look at properly embedded.
So you're saying it's not bounded away to 0. You're taking points where the injectivity radius goes to 0.
Right, but those points can go to points in the manifold where the ambient injectivity radius at those points is very small.
Sure, but I'm saying they cannot accumulate in the ambient manifold.
They cannot accumulate in the ambient manifold, in particular, but the surface itself cannot accumulate because it's proper. The immersion itself is always proper. Okay, so yes. Anyway, very simple. There's nothing deep about anything I'm proving here. It's just using the basic definitions and this one little estimate I said, which is a local estimate about estimating intrinsic area growth in the presence of being inside of a exponential coordinates. The coordinates shrink, the estimate gets worse and worse. So as long as the ambient space has positive injectivity radius, then you see that you have to have a certain amount of area on the disk of some very small epsilon radius. Its area has to be at least some number times epsilon squared. It has to kind of grow like quadratically on a small scale. Okay, as long as it has mean curvature bounded in absolute value by mean curvature function bounded by some constant. Otherwise, it's not true again. Right? Very thin cylinders, their area growth is very small. Right? Cylinders are small radius. Anyway, okay, so but it's a general result and definitely food for thought. Okay, so I wish I had prepared this really yesterday instead of this morning. Right, so for example, if you have finite topology in one end, then finite topology, each end is an annular end, right? Right. So you can say things about the thing. I mentioned it before, but I didn't say it here today. In general, suppose you have a complete three-manifold that's locally homogeneous. That means locally it's isometric to a homogeneous, one of these special geometries that you have, like R3, with a homogeneous metric, like metrically grouped, for example. So you have a local homogeneous structures, locally homogeneous. What can you say about minimal surfaces in it of finite topology? Well, I don't know. This is telling us something. That last theorem was telling us something. But let's throw in the extra word, complete and embedded. So a complete embedded surface that's minimal of what do you call it? Okay, complete, embedded, minimal, right. Well, it turns out that all these surfaces, that when they embed in these nice manifolds, they have a nice local structure, they have a very neat property. Is the closure has the structure of a lamination, so a minimal lamination. So that gives you, minimal laminations have the property, they have locally bounded second fundamental form. So this, the kind of question that we were just looking at, when you, and they have, if you want, what's called locally positive injectivity radius. So when they're embedded and the annulus is embedded, in fact, in little balls in the space, the injectivity radius stays positive in little balls. Surface keeps coming back. The injectivity radius function of the surface, when it restricts to a compact part of the manifold, it's bounded away from zero. So that's a global result I proved with Joaquin Perez. Okay, right. So I'll just mention some of this. This slide partly came out of some work I was doing with Alvaro. And we're trying to prove that in the manifolds that Laurent and Harold look at, which are finite volume hyperbolic three manifolds, in that case, we can prove that a complete embedded finite topology minimal surface has bounded second fundamental form. We would like to prove it's always proper. I don't know, maybe it's not true, but that's that we just started working on it just a little bit. So we would like to prove that finite topology minimal surfaces are sometimes, in fact, properly embedded. And once they're properly embedded, you can say lots more things. Okay, so where was all this going? Trying to understand the local geometry of surfaces, and we're trying to understand local invariants, local properties like injectivity radius, and associate them to global questions. Okay, so In particular, suppose you have a nice three-manifold. So say positive injectivity radius, kind of looks like Euclidean space up to a bounded deformation of the metric. You have this kind of space like hyperbolic space. What can you say about minimal surfaces in it? When that minimal surface has finite genus, or genus 0. Let's even be really more specific. What do minimal planes look like in such a surface, such a manifold? Look, take an embedded minimal plane. What can you say about it? Okay, so this theorem is supposed to tell us something about what it looks like, at least on the scale of the injectivity radius function. So in other words, this theorem is stated in a manifold which is R3 with its usual metric. But everything that comes after the first sentence really has very little to do with R3. So it's really telling us something about all what are called homogeneously regular three manifolds. Okay, so it says, suppose you have a surface in here, like our annular end that we were looking at before, and suppose the injectivity radius of the surface is 0. That means we have these very, very short loops in it. Very short loops, okay? Now, if you're in a genus 0 surface and you have a loop, genus 0 means it separates, right? Every simple closed curve separates. So these little loops are separating the surface, okay? Okay, then it says, I can find a sequence of points in the inside of our surface that lives inside of R3, where the injectivity radius function at these points goes to 0. That's, for sure, that's the definition of the injectivity radius function being 0. There are points where it's very, very small. Okay, so there's certainly points like that. But I want some more properties on these points. And they're going to be, right, I'm going to tell you a little bit more about these points in a minute. But okay, then for all n, okay, so I want to let me draw a picture. Okay, so we have our surface in space, whatever it is, genus 0, but we have these loops. So we have Pn, and at Pn we have our short loop. Remember, minimal surface in R3 has non-positive Gaussian curvature. In those cases, we can create these little loops. So the injectivity radius having a certain value, small, means twice that small number, there's a loop, a geodesic loop of that length. So we have a loop. Here we have the nth loop, we have the n plus first one. We have these places where it's very, very short. So we have some p n plus 1, okay? And we have our little geodesic loops at all these points. So I'm going to translate the surface. So I'm going to try to think of how does it look in coordinates around this point. So either I can just put a ball of some radius around this point. This ball is going to have radius n. Well, k. I guess k in general. I could maybe put the same n. It's a question of finding these. Okay, so I'm going to put a ball of radius n centered at these points. Or if you want, translate the surface back to the origin. So I translate back to the origin, and now Pn is like at the origin. And I have my loop. Here's Pn hat at the origin. So I can translate this ball back to the origin, or I can just kind of try to say, what does it look like inside this ball? So the first property is that I can pick the points, okay, so that when the surface, I look at how it intersects this ball of radius n. I stated it quite slightly different, based it here. So I look at the ambient ball. Then I actually intersect this ambient ball in a compact set after expanding it. So maybe I should. Okay, so our surfaces are actually lambda n, m minus pn. So I actually have to do a homothetic expansion. So this ball is not radius n. So I take the surface, I translate by pn, I scale the surface. Then the claim is in the ball of radius n, here, ball of radius n at the origin, what I see is a surface that passes through the origin, and it's compact with boundary in the ball. There's a component of the surface in the ball of radius n going through the origin, and its boundary lies in the boundary of this ball. Okay? So after rescaling, now what does this rescaling do? It's rescaling so the new injectivity radius function. So when you scale, when you take a surface in R3 and you scale by 5, the injectivity radius function scales by 5 also. Right? Geodesics are still geodesics. Every exponential map really hasn't changed. It's just how far you've gone. So this rescaling has the property that this geodesic loop now at the origin has length 2, I guess. So instead of having, so I scale by the injectivity radius function, now this geodesic loop has length exactly 2. So that's one of the properties this scaling factor has. I didn't tell you yet how to find these points, but anyway, the claim is you have these points. Then the question is, what do these compact minimal surfaces converge to? Remember, they all have genus 0, right? So if they converge to a genus 0 minimal surface, it must be one of our classical examples. And the classical examples were the plane. Well, it can't be the plane because it's not plane simply connected. The injectivity radius function is 0. So it has to be the catenoid or Riemann. And that's what the theorem says. It says, I get a catenoid, I get Riemann, or I get one of the limits of Riemann, which is a parking garage structure. So either I get, so the possible limits are the catenoid, Riemann, or a parking garage structure, in other words, a foliation of R3 by parallel, say, horizontal planes, if you're after rotation, and 2 vertical lines in it of distance 1. Okay? Separated by distance 1. So, and one of those lines goes through the origin as well. So, okay, so how do I pick my points? So that's what, in other words, at certain points, what looks like under a microscope at these points is very, very classical. Either I'm seeing something like a catenoid on a very small scale at these points, I'm seeing Riemann on a very small scale, or I'm seeing a parking garage structure on a very small scale. That's what this theorem is basically saying. And when I say parking garage structure is, as I get to the limit, it looks like helicoids along these lines. I'm getting spinning just like Riemann. They're spinning oppositely. And I get this sort of structure. Okay, so let me tell you how you find these points. This is a very, very important scale because you don't have to know how to prove this. You just have to know how to use it, right? So let's think about that. Maybe we'll talk at some point a little bit about the proof here, but later in the course. But it's a great tool. Okay, it's a great tool, and it's really a tool that, for example, Alvaro and I use for proving this, for understanding, for example, complete embedded minimal surfaces, a finite topology, and certain hyperbolic free manifolds. For example, you could think of using it lots of different places. Okay, so let me just explain what these points, how do you get these points? Any questions about the statement? Okay, so these points, so I have to tell you how to find the points. So Pn is a point of what's called almost minimal injectivity radius. Okay? All right, so what does that mean? So I'm going to pick these points in a particular way. So initially, okay, so I should have said one more thing. If it were the case that the injectivity radius function of m was positive, then I could apply a theorem that Harold Rosenberg and I proved that implies such a surface is properly embedded. So if you have a complete embedded minimal surface in R3 whose injectivity radius function is positive, injectivity radius is positive, it's always properly embedded. In which case it would be a catenoid, it would be a catenoid or Riemann example by classification. So we must be in a different situation. We must be in the case where the injectivity radius is 0. That's that part of the hypothesis. But we're scaling to try to make it more uniform. Okay, so we want to find these points, special kinds of points that are described in the theorem. So since the injectivity, so let's look at the injectivity radius of m is 0. What does that mean? That just means there are points qn on m. And of course, they're going to go to infinity in the surface because, well, anyway, so I want the injectivity radius function of m at qn is, well, much bigger than n, right? I'm sorry, 1 over it. 1 over it is much bigger than n. The injectivity radius function is very small, so 1 over the injectivity radius function is very big. And remember, these are the numbers we're going to scale by. Okay? And I restrict myself at these points. Here's a point qn. I restrict myself on the intrinsic. So I look in the intrinsic ball centered at qn of radius 1. So that may or may not be a disk. I'm looking at a point. Well, it won't be a disk, I guess, in general. Anyway, so I restrict to here, and I create the following function. So let me see. So you write down the following function. Hope I can do this well. So function x. Okay. So you take a point x here. Okay. In this ball here, and I define to be the distance from x to the boundary of our ball. Okay, on m. Okay, and I divide by the injectivity radius function at the point. Okay, oh, it should have been x here. X here. Okay, so we have our ball. I look at the distance from the point x to the boundary of the ball. That's this number here. So it's 1 minus, if you believe this is like sort of like the norm of x, anyway, that distance. So you have so you have x. We have this number divided by this. Okay, this function has a property. It's 0 on the boundary of the ball. So this function here is 0 here, and it's this value at the origin. Because the distance, if you put qn here, the distance from qn to the boundary of the ball is 1. So we get 1 here, and the injectivity radius function at q is this very, very big number. Okay, so it's very big here, and the point Pn is a point where f is greatest. Okay, so that's how you pick these points. So this function has a maximum value at some point, and we call such a point of almost maximal curvature. So when you pick it so that this is huge, really, really big, then that's how we choose the points. And that's how we get this result. Okay. So I don't know if there are any questions, but this is at least you have it there. It's very useful to quote it, even if you don't know how to prove it. So it says on a small scale, we have a universal picture of what the geometry looks like at certain points. Either it looks like a catenoid, looks like a Riemann example, or it looks like a parking garage structure, like so multi-graphs, and they're spinning like we do on a parking garage structure. Okay. All right. So one of the things we'd like to know is we'd like to know finite genus, complete embedded minimal surfaces in R3 are proper, right? And if they were, we'd have a very nice, would be a nice theorem. Particular genus 0, we'd have a complete classification of these surfaces, because positive injectivity radius means properly embedded. So that would be nice, and how the local geometry influencing the global one. Okay. And we know it in certain cases. So if the original surface has a countable number of ends, so it's not like a Cantor set removed from the two-sphere. Okay, it has some control on its topology. That's true if and only if the surface is properly embedded, if and only if it has bounded Gaussian curvature, if and only if, remember the Gauss formula, if and only it has bounded second fundamental form. So everything is controlled somehow if the topology were controlled. Countable number of ends. Almost certainly has nothing to do with having a countable number of ends. Of course, one case of a countable number of ends is a finite number of ends. And that was proved by Kolde and Minicurso. So they have a paper in the Annals where the main result is proving this result when you have a finite number of ends. So complete embedded minimal surface in R3 of finite topology is always properly embedded. So, okay? So if you take a plane, try to put it into R3 in a complete way, well, a plane has finite topology. Therefore, it's properly embedded. Once it's properly embedded, you have good techniques. In particular, you can prove it's a helicoid or a plane. So that's there are these consequences of knowing properness. So that's why that's really an important result. Question? Okay, so now I'm coming back to sort of the more beginning part of my talk. Remember, we were trying to understand what is the shape of minimal surfaces. For example, we had that particular case where we had two curves in parallel planes. Think of two Jordan curves in parallel planes. What are the shapes of those minimal surfaces? Well, if you have convex Jordan curves, then the claim is it must be an annulus. Okay, so let me draw a picture. And I got a few minutes to talk about this. Okay, so this is a great problem, at least to think about sometimes. So I have two parallel planes. I have convex curves. And I'm looking for minimal annuli that bound those two curves, or minimal surfaces in general, compact minimal surfaces. And the claim is it must be an annulus. Or it could be disconnected. It could be two disks. But if you look at a minimal surface that's connected, the claim is it must be an annulus. Great problem, and almost everybody's tried to do it. I would say it's true, but I don't know. Nobody's proved it. Okay, so what do we know in certain cases? Okay, so a little thought is Morse theory. Okay, if you have a minimal annulus and I intersect with horizontal planes, because the index of any kind of critical point here is 0, it's not hard to see that, or from the topology of annulus, it intersects each plane in a Jordan curve. So here we're convex, or even when we're convex, it's a Jordan curve, convex. And what Schiffman did, he proved that each of these immersed curves is in fact a convex curve. In particular, the annulus is embedded. Wasn't so obvious back then, right? So we have this sort of picture that we get a convex curve, and I'm pretty sure that next time I'll go through the proof of that. It's elementary. You need to know a little bit more about minimal surfaces, coordinate functions, or harmonic functions. Once you know that, you're pretty much, and the Gauss map of a minimal surface is conformal. It's just a little bit of knowledge. It's not hard to prove this first result of Schiffman's. So that's certainly a very nice thing I'll go through, hopefully next time, and I'll go through that proof, give a complete proof, give his proof. Then actually the original conjecture I made was at a conference in Brazil, in Fortaleza, 1970, 77 or something. Well, 78 maybe, 77, 78. And actually I posed that question and I posed this question. So I gave a course on minimal surfaces. I think IMPA's library still has a copy of the lecture notes. Right, and it's got lots of unsolved problems in it. It's got about 50 some unsolved problems about minimal surfaces. Some of those have been solved. But one of the questions was this first one, and this more general case. So first case, and the conjecture was a Jordan curve here and a Jordan curve here. So now I'm going to make it a little bit more complicated. I also want convex curves here, so convex curves, but maybe I can have more of them. I can have a whole bunch of them in this plane. But I want them not to be inside of each other. Then the claim is, again, you have to have genus 0. Okay, there's a picture, right? So the claim is convex bounding, or curves bounding convex disks. Pairwise disjoint convex disks. Also, the only possibility is genus 0. There's no handles, there's no topology. So not everybody is aware of this problem, but still nobody came up with any counterexamples yet. Okay, and then there's another thing. We like to always classify all the examples. Since we don't know, you don't have higher genus, we believe there are no higher genus examples, we don't know how to prove that. So let's assume we have genus 0. That means we're looking at annuli. So we have two convex curves here, and we want to classify the space of all minimal annuli. And again, I'm going to at least sketch the proof of that. I'm sorry. Right. Oh, right. I guess in general, that same conjecture and even this conjecture, they both should hold when the curves are what are called extremal. So I won't do the, so in other words, if you're willing to, instead of take a half plane, draw a picture. Suppose you have the two Jordan curves that lie on the boundary of a convex hull. So here's a half plane this way, and then I have a tilted plane. So this plane is not parallel to this one. But on this plane, I have a Jordan curve. On this side of the wedge, I have a Jordan curve. This side of the wedge, I have a Jordan curve. Then you look at the minimal surface you get. Again, it has to be an annulus. You can't have higher genus, okay? Okay, so you can think of this as a generalization, but also a generalization where you can completely understand the moduli space of genus 0 examples. Okay, so, and that's, I think I said that in the next part. No, I didn't say it, so I'll say it here. Okay, so I'll say it in a few minutes, I guess. I guess I'm not going to say it in a few minutes. I guess I should go right here. So I'm going to talk a little bit more about this problem next time. There's more things I could say about this kind of problem. I think go to higher genus after that. So I'll talk a little bit more about this problem, what we know about it, and then sort of continue with more classical examples, and hopefully really get to the definition of minimal surface next time. I mean, a complete, nice definition. And that's it for today, I guess.